Hey folks, welcome to the next episode on Clear My Paper. Today we are going to talk about understanding some of the patterns and symmetry on what makes matrices and determinants beautiful and the general underlying beauty that normally gets missed while applying matrices and determinants to solve the problem. So how are they kind of in a condensed way or in a short way represent so much of rich information? Let's unpack some of those. And as a quick reminder, if your intention is to just clear your paper, you can skip this video and move on to the next, which is relevant just for the examination purpose. But if you want to just get some intuition, clear your head, and just interested in what's going on behind the scenes, you're more than welcome to watch this episode. And as a quick prerequisites, before you understand this, you need to check out my previous video that I had put on the algebra behind the 3x3 matrix and the related determinant. This is more of a continuation to that video. And I've also put the name of the episode on over here in case you want to check out before that, so that will help you in understanding. So what are we trying to do here? Okay, so let's do a quick recap of what we did last time. So in the last few episodes, what we did is we tried to solve the 2x2 matrix, which is two equation and two unknowns. We did it with actual numbers, and we also did it in a generalized format where we use the variables a, b, c, d, and we kind of defined and we derived the determinant of a 2x2 matrix in the context of finding the values of x and y. And this is where we reached, where we figured out the denominator should not be equal to 0, and the denominator AD minus BC is nothing but the determinant of a 2x2 matrix, and which is what we kind of defined here in the matrix and determinant notation, if you see here. And the same thing we did in the last video for a 3x3 matrix, which I have defined on the right hand side, and we did the same thing, and we kind of figure out the value of x, x1, x2, and x3. We did that, right? So we were there, and I've kept it here for quick reference purpose. If you remember, if you have checked out my last video, we had done kind of a lot of lengthy way of algebra where we multiplied with a combination of variables to find the value of x, y, and z, and we came to this conclusion over here of how the x1, x2, and x3 values are determined, and whatever is in the denominator, they are the determinant of that, and the determinant is same regardless of how it appears in terms of variables. So I'm going to copy and borrow all the values that we derived for x1, x2, and x3 in this video also, so that it helps. And this is where I've copied it. Okay, so in case you are not sure where this has come from, please check out my previous video. So let's focus on the 2x2 matrix for a minute and get some kind of intuition, and then try to apply that on the right hand side for the 3x3 matrix. So let's focus on the 2x2 matrix. So if you see here, so you have the denominator as AD minus BC over here, which is same as what's written here, AD minus BC. And if I represent that in the matrix format, this is what I get. If I represent it in the matrix format, that's what I get, because if I represent this in matrix format, it's a simple A, B, and C, D, where I'm defining the coefficient matrix for this particular equation, which will come like this. So there is a strong correlation between the way this appears here, the sequence of terms, and the way the determinant is defined, which we derived algebraically. So if you see here, the determinant is AD minus BC, and if you remember the 2x2 matrix explanation that I have put a few weeks earlier, we defined that its determinant of a 2x2 is nothing but the product of the diagonals and the differences. And the way you take the diagonals is you take the diagonal on this side, which is on the backslash, then you do on the forward slash first. Okay, so you take the backslash AD, then subtract, and BC. That's what we do. That's how it is. Another way of looking that is there are two or three things interesting here. So if you take this whole ABCD that I'm writing here, A, B, and C, and D, right? Although it's a 2x2 matrix, the way this AD minus BC, the determinant, is defined, the way you can think about that is this A is a coefficient or a scalar, and it's multiplied by a matrix with only one element, like a determinant D. Similarly, B is a coefficient or a scalar if you guys hope you guys remember what is a scalar. Just it's a number that kind of scales up or scales down, and C is kind of a determinant of a one by one matrix, because that's possible, right? If you take a number, any number, or in a matrix format, let's say a matrix just has one row and one column, say the number 4. In this case, since there is only one element, the determinant of this matrix is the number by itself. That's what it is, right? So in that context, when you are multiplying this and this like this over here, A into D as the first term, you can think about one of the data elements on the matrix is getting multiplied by a determinant on the lower row, which is, although this matrix is a 2 by 2 matrix, this one is a 1 by 1. So you're stepping down on the order of the matrix. So you can think about, you take the coefficient and you multiply by a step down order of the matrix. So from the 2 by 2 matrix, you're forming a 1 by 1 matrix and multiplying it. Similarly, over here, you are using a scalar. Then you're seeing across the board what is the sub matrix or the step down matrix, and then multiplying the determinant of that. In this case, the determinant of matrix C will be C itself. So that's another way of looking at this AD minus BC on what actually it's doing. So it's like it's having an effect of a scalar being multiplied by a sub matrix of a lower order than the given matrix. If the given matrix is 2 by 2, the sub matrix over here becomes 1 by 1. So you can keep that concept in mind, and we'll apply the same thing on the right hand side for the 3 by 3 matrix, because that's more kind of difficult to understand, and that's the whole purpose of this particular video. Another thing that you notice is the minus sign here, the minus sign. We know that the minus sign was derived algebraically, so the negative sign does come in, and that's not a problem. But if you'll see, there are some nuances about these signs in the 3 by 3 matrix. But as long as we remember where did this algebraic signs come from, we will be fine. Okay, now let's switch back to on the right hand side and apply the same kind of intuition and try to understand how the 3 by 3 functions in this context. So we have the same equation that we solved in the above problem or in the previous video, where we have 3 equations and 3 unknowns, but it's in the generalized format of ABCD as opposed to the numbers. And I've just written this the coefficient matrix just for quick reference, where I'm just taking the coefficient on the left hand side and writing it in the in this format. And I borrowed the derived values or the solutions of equations for x1, x2 and x3 from the previous set which I showed you when I scrolled up, and that's written in the numerator and the denominator format. In this video, we'll just focus on the denominator part, and in the next video we'll come to the numerator part. So the denominator part is nothing but the determinant of this coefficient matrix over here. This is the coefficient matrix over here. In this case, this is the coefficient matrix. So this is the coefficient matrix. The denominator for x1 and x2 represents the determinant for this coefficient matrix A. So always remember that, and the value is going to be the same. And regardless of how the sequence of variables in the denominator appear, they might appear that there are too many variables coming back and forth for x1, x2 and x3, but the value is same because the determinant of a matrix is going to be constant. It's going to be the same. Okay, and let's focus on the denominator, and let's find some of the interesting patterns which come, and then how that naturally leads us to definitions of some terms and terminologies in the world of matrix and determinants. Okay. So what is the first thing? What is the first thing we notice? The first thing we notice here, just focus on the denominator for now. If you see the variables outside the brackets, right, which is a scalar, like how we did it here. So it's like you can think about this as A multiplied by D, something in the brackets or braces. Similarly, we have brackets here and we have something outside the brackets. So whatever we have outside the brackets or braces, you can think that up as a scalar or a number that's multiplying. And the interesting thing, which is the first point, is the algebraic signs, the positive and negative, are alternating. Just like here, if you see here AD minus BC, this is the positive sign and this is a negative sign. So positive, negative, something like that. So there is the alternation, and that comes because the way it was derived from the algebraic part, which we should not forget. So that's the mystery behind that, how it was derived, where it was a simple solution. Similarly, that particular property has been retained. But since the number of terms are more here, you can appreciate and visualize the alternative pattern throughout the equation. For example, we start here with plus, If the starting is a plus positive sign, then the second one is a negative, then the third one is a positive. And if we had a higher order matrix of 4 by 4, the next one would have been negative. So the algebraic signs are alternating. Whatever is the starting point, then it alternates. It could be positive, then, or it could be negative, but it's going to be alternating, just like here. In both these cases, it starts from positive and then alternates negative, but it could be vice versa also, which we'll see. That's the first observation. And like I said, that comes because of the way this equation was derived, whether it's a 2 by 2 or 3 by 3. So keep that in mind, and we'll kind of trying to condense it later, but you should understand why this alternating sign, and that's the reason I'm trying to emphasize that this algebraic signs are alternating because of the algebraic way of solving the problem in finding the value of x and 1 and x2 and x3. But when you actually apply it in the actual case and during the finding a problem to a determinant of a 3 by 3 matrix, you don't have to really figure that out, where did it come from, as long as you understand how to apply the alternating signs, which one will have a positive and which one will have a negative. That's what is important, and which we'll come to that in a minute. The second part is the symmetry. If you check out the numerator and denominator for all the values, the items within the brackets are the same, only the coefficients are varying. If you see here, right, this is same, this is same, this is same, and this is same, and this is same, and this is same. So that's a symmetry that we are talking about in the title, right, which is a symmetry over here. We're talking about symmetry here, and that's a beautiful symmetry that we are trying to figure out, and it kind of helps us in a way that will become evident. But since we are not focusing on the numerator in these equations, don't worry about that. But when you do a Kramer's rule problems, the numerator kicks in, and that's when you appreciate the symmetry between numerator and denominator, how that comes handy, and how that is a natural segue to solve solutions using Kramer's rule. But let's come back to denominator. So that's the second part I wanted to highlight. And the third part, I have just extracted the denominator only because we are going to focus on denominator for the time being. So I have extracted the denominator, this one, and I have rewritten it over here. And like I explained in the 2 by 2 matrix, where we can think about a step down, a sub matrix multiplied by a scalar, we can do the same thing for a 3 by 3 matrix also. So if you just focus on the denominator here, there is a coefficient, and it's multiplied by this. So this whole piece itself looks like a 2 by 2 determinant, like how you have AD minus BC here with 4 variables. This also has 4 variables, and this pattern matches with the 2 by 2 matrix. So we can think that as in a way that there is a scalar that is being multiplied by a 2 by 2 matrix, and hence this particular thing can be expressed in a determinant format, just like how you have expressed the 2 by 2 here. So this piece over here can be expressed either way. This is the determinant format, and this is post multiplication in the algebraic format. The same way, if you kind of break this down, this whole piece can be expressed in this way. This whole piece can be expressed in this way. In whole piece can be expressed in this way, and each one has a scalar multiplication. And the same way like we did in the 2 by 2 matrix, where we thought that when we multiply A into D, although the given matrix is of order of 2 by 2, where they have 2 rows and 2 columns, this is 2 by 2. But when we look into this in this fashion, we kind of assume that a scalar is being multiplied by a submatrix of a lower order of 1 by 1. Similarly, when we express in this format, we can think about a scalar matrix being multiplied by a determinant of lower order, and the lower order in this case is 2 by 2 because the order of the main equation is 3 by 3. This is a 3 by 3. There are 3 rows and 3 columns, and the submatrix or the scaled down version will become a 2 by 2. So this becomes kind of a 2 by 2 matrix, a scalar multiplied by 2 by 2 matrix, a scalar multiplied by 2 by 2, a scalar multiplied by 2 by 2, right? In all across the board. And the signs keep alternating like I discussed. If this starts from positive, then there is negative, and then there is positive. So you can think about from that format, and we'll solve a couple of examples or we'll kind of explore more when we find out the x2 and x3 variable to make that as clear. So these 2 points also are interesting, right? Thinking about for a 3 by 3, thinking about how a 2 by 2 submatrix is formed, and how are we kind of taking the coefficients and thinking them in a scalar format where it's a simple multiplication. So hold on to that thought, and we'll try to apply the same thing in a different format, or we'll just try to explore that more while we do the x2 and x3. Okay, let's keep going. Okay, so now I've taken the x2 and I'm going to x2 we have derived from the previous episode, and we are going to focus just on the denominator, not on the numerator. And although you see the denominator looks different than the x1 over here with all the variables which are resequenced completely, but the answer is still going to be the same because that's a function of a determinant. It's a property and it does not change, which we have seen earlier also, just like in 2 by 2 or when we solved it algebraically. Nevertheless, moving on. So another way of looking at the same thing of the scalar and submatrix, let's define it here. Let's focus on the let's just focus on the denominator here, which is the denominator or the determinant, which is minus b. Again, if you see here, the signs are alternating. It starts with negative and then positive and then again negative. So it starts with negative. I've broken it down, positive and negative. I'm going to write it in the scalar and the submatrix, this whole thing, just like how we explained. So first I've written down all the scalars, minus b, and then I have plus e, and then I have minus h with alternating signs. And whatever is in the bracket can be viewed as a 2 by 2 determinant because we are stepping down, we are forming a submatrix. And just like how we had AD minus BC here, we can express in the same format in this fashion. So we are going to express in this format. And how do you express that? So you have DI minus FG. So I know that there is a cross multiplication. So D will be here, I will be here, and F will be here, and G will be here. So that way it's DI minus FG. This matches. Similarly over here, it's AI. A is going to be here, and they are going to be on the diagonal, excuse me. And then C is here, and G is here. So AI minus CG, this also matches. And over here also it's A and F and C and D. So if you see AF minus CD. So you can think about a scalar being multiplied by a submatrix which is of one order lower than what the input matrix is. The input matrix is 3 by 3 and the submatrix is all 2 by 2. Okay, you can think from that standpoint. So that's another way of interesting looking at the symmetry on how you should think about this formula. And the interesting thing is, if I give you a 3 by 3 matrix just like this and I ask you to find the determinant of that, how will you know what variables to use? Because these formulas in the denominator for x1, x2 and x3, they are not very user friendly to memorize, and that's what we are trying to come at. If you understand this alternating signs and how a scalar and this submatrix is formed, if you're so far with me on that, now let's define how to memorize this in an easy way for matrices. So if you look at here, what's happening? Just focus on the scalar, the thing that the number that is outside the determinant, which is b, which is e, and which is h. And for the time being, don't worry about the algebraic sign, that will always alternate. Just focus on the value. So what's happening? How it is defined? So if I take this matrix, okay, over here, and the scalar is b, and I've circled the scalar as a b, how am I forming this determinant? What is the trick to that? So what I've done is, if you see my highlight in yellow, I have highlighted the whole row in which b is present, and I have highlighted the whole column in which b is present. So I've highlighted the row and the column in which b is present, which is this and which is this. And what does it mean? That's a first row. B is in first row and second column. I have highlighted that. So I know that. And what I'm trying to do is, if I want to find what is the determinant that I need to find, if you see there is no b element here. So what's happening is, in a way, if you look at this, the way to remember that is, whatever row and column which is highlighted in yellow where the element is present, if you exclude that, disregard that, ignore that, and form a determinant of the remaining elements which are not highlighted, which is D, G, F and I, that's what you get here, D, G, F and I in the exact sequence. D is below G, D is below G, and F is below I, F is below I. That means the way to find determinant is take any element as a scalar and multiply it by the remaining elements in which the very element that you selected to start with, that row and that column is excluded. In this case, we are excluding the first row and the second column. Similarly, over here, if you see, it's multiplied by E and there is a determinant. So let's take the scalar which is E, and if you see here, I've just copied the same thing, what is written here in here. So the way it's functioned, okay, I am going after the E, the scalar is E. So I'm marking the row and the column where the data element E is present. In this case, E is present in second row and second column. So it's second row and second column, and I highlighted that in yellow. So I need to form a determinant of all the remaining metric of the remaining elements which is outside this highlight of yellow, which is A, C, G, I in the same sequence. So A, C, G, I. That's how it is formed. So that's another way of thinking about this, that how you kind of form the matrix. Just like in a 2 by 2 matrix, when you write AD minus BC, you can think about A multiplied by D, it's single element, right? And B multiplied by C, the single element. The same way, you are kind of breaking it apart and you're trying to understand in a visual way, how do I remember this formula, or how do I do the calculation while I determine the determinant of this matrix, because you cannot obviously remember this formula, which is all mumbo jumbo for each one of them. Similarly for H, right? I've taken the H here. I'm going to highlight it. So it's AC and DF here. So it's AC and DF. Sorry, it's DF. It's DF. My bad. Okay. So if you see here, I've highlighted the H, which is a scalar outside the determinant, and I'm marking the row and the column, which is a third row over here, and which is a second column over here. I'm going to cross that out. I need to exclude that. And whatever is remaining, right, I'm going to just write that inside the determinant brackets or vertical lines in the same sequence, AC and DF, AC and DF. And then I'm going to treat this as a 2 by 2 determinant. So where I take H and I just multiply the diagonals starting with the backslash, which is AF minus CD. And that's how you get the determinant over here, right? Over here, if you see AF minus CD. So that's another way of looking at that, which will help you in remembering why this is coming from, where this is coming from, and how do you remember that in the exam. And as long as you remember how to form this in the exam, you don't have to really worry about the sequence. And the same thing for X3 also. If you focus on the denominator, I put in adjacent fashion, so that it's another way of looking at that. So I've taken the X3 from the previous episode. I'm focusing on the denominator, okay? And I'm going to take each of the scalar vectors here, C, F, and I. And again, if you see, the algebraic signs are alternating. We have plus here, then the next one is minus, and then there's a plus for the reasons I have explained. So I have formed 3 matrices, and I'm going to form 3 submatrices, because when I ignore this, a 3 by 3 will have a 2 by 2 determinant. It will scale down, or it will step down, or it will be a submatrix, right? So we have a C here, we have a minus F, and we have a I here. And how do I form the submatrix for this? So I'm going to figure out where C is. I'm going to highlight that. I'm going to cross or highlight the row and the column where C is. In this case, it's the first row and the third column. I'm going to highlight that. Whatever is the remaining elements outside the highlight, I'm going to form the determinant in the exact same sequence as it comes. In this case, it's going to be DE and GH. Similarly, the scalar outside the determinant is F. I'm going to highlight that, which is the second row and third column. Whatever is left over, I'm going to form a determinant out of that, which is a 2 by 2 submatrix. Similarly, over here, I will have a 2 by 2 submatrix. And then I'm going to just cross multiply to get this exact denominator. Okay, that's how you find out the determinant of a 3 by 3 matrix, by forming that, the notion of submatrix and all those things. And the beauty is, for finding a determinant of this, right? Finding a determinant of this, it does not matter what is the sequence you consider. You can take any row or any column. What do I mean by that? For example, since the determinant is going to be the same, for finding out x1, if you see finding out x1, the scalar is A, D, and G. So it looks like I am taking this particular column. I'm going to find the determinant or submatrix for this element, this element, this element, all the elements in column 1. That's what I'm trying to find. But if you take x2, and if you see the value is minus B, E, and H, looks like I'm targeting the second column, and for each of the elements in the second column, I'm forming a submatrix. But if you take the x3 over here, looks like I'm targeting the third column, because if you see the coefficients here, C, F, and I, it's C, F, and I. It looks like I'm targeting the third column. So for each of the third columns, I'm trying to form a submatrix. But the answer of the determinant is still the same. So basically, it does not really matter that any row that you pick up, since it is a 3 by 3 matrix, it's a 3 by 3 matrix over here, right? It's a 3 by 3 matrix in the given format. You are free to choose any row. Any row. There are 3 rows and there are 3 columns. You are free to choose any one row, or you are free to choose any one column. Any one thing you pick up, whichever is comfortable. Either you choose a row, either you can choose this row or this row or this row. Sorry, these are columns. Either you can choose column 1, column 2 or column 3, or you can choose row 1, row 2 or row 3. And then you apply this trick of taking each element and crossing out the row and column where it belongs to and finding the determinant of a smaller submatrix in this fashion and multiplying it by a scalar. So that's kind of the thing that you need to remember, and that way it will become very easy for you. So that's kind of the key takeaway. So that's what I wanted to kind of plant in your head and how to think about it. And I'm going to write down the formula here in the concluding part. If you see here, I've written down, I got this image from the Google, from some website, I've copied it. So if you see here, there is a 3 by 3 matrix here, 3 by 3 matrix. And in the explanation that I gave above, I was targeting all the columns. In this case, they're taking the first row to find the determinant of this 3 by 3. So they're taking the first row, meaning they're going to target each of the data elements in the first row one by one and try to find a determinant of that as a submatrix. And if you read it from bottom to top, what happens is the first element is A. So they're going to take A, and whatever is remaining, if I cross out the row and the column where A belongs to this row and A belongs to this column. If I cross out that, whatever is remaining in the purple or a lavender color, I'm going to form a determinant of that multiplied by A as a scalar. So if you see A and there's a scalar multiplied by that. And since A is positive, we'll come to the alternating signs, how to put that, but there's a sign that is alternating. So A is positive, so B is negative, and then C is positive. So alternating signs. Similarly, since I've selected the first row, I'm going to select the second element on the first row, which is B. So I'm going to cross out where B belongs to. B belongs to the first row and the second column. Whatever is remaining, which is in the purple color, I'm going to multiply B by the determinant of whatever is left over in the purple color in the exact same sequence. Similarly, the last element is C, because C belongs to the first row and that's the last element. So I'm going to cancel out the row and column where C belongs to. C belongs to the first row and third column. I'm going to cancel that out. Whatever is remaining, I'm going to multiply that as a determinant to C. So I have C here, then I have the determinant opening up, and I'm going to exactly copy the same sequence and find that. And then after here, I'm going to just treat this. Now I've created a 2 by 2 submatrix here. I've created 2 by 2 submatrix for a 3 by 3. And then I'm going to treat this as a 2 by 2. And I know how to find the determinant of 2 by 2, which is nothing but multiplying it diagonally, starting with the elements on the backslash first, followed by the forward slash, which is what it is, EI minus HF, DI minus GF, this multiplied by this, again this multiplied by this. And the signs for the determinant, which we'll explain in the next video, they are alternating. If it starts from positive, then there's negative, and then there's positive. And then finally the determinant of this whole equation is this. So we started off from this. This is hard to remember. So from this we slowly came to this, which is easy to remember. But when you compute, you go back to this. There is a final value there will be some value here which needs to be computed. But remembering this will be difficult. So if you start from here, then you take this step first, and then you take this step first, and then you go to the answer. It will be easier instead of starting from here. But for explaining why it comes, I took a top-down approach so that you get behind the scenes what's happening. Pretty much that's what was the objective of this video, and I'll just summarize the key learnings. So for finding a determinant of a 3 by 3 matrix, you can choose any row or any column. It does not matter. The answer does not change, and the answer should not be 0 if the solution has to exist. The notion of submatrix, which is what I explained, right? You form a submatrix or a scale down, and then you give it the effect of a multiplying by the scalar. That kind of leads to a definition of something called as minor. Basically, this submatrix is called as a minor, and we'll talk about that in terms of terms and terminologies in the next video, but that's what it is. There's nothing more to that. Every submatrix is called as a minor, which is nothing but whatever scalar or coefficient variable you're choosing outside determinant. When you eliminate that row and column, whatever you get remaining is a submatrix. So whatever is in purple color here is a kind of a sub matrix when you form this. That's one. So for a 3 by 3 matrix, you'll be forming a 2 by 2 sub matrix. For a 2 by 2, you'll be forming 1 by 1. So you'll step down or you'll form a scale down. And that is what, that's one. And the interesting thing that we still need to discuss in the next video is alternating signs. We know why the signs are alternating because of the algebraic derivation and all those things. But how do we remember, just like how we remembered how to calculate the matrix, when we should think about what will start from positive and what will start from negative and how do we alternate, that we have to figure out, and that we'll talk about in the next video. And that alternating sign has the term called as cofactors. That's the definition of cofactors. So we are just planting the seeds here for some important terms. We will talk what is a minor, we'll talk about what is a cofactor. And last but not the least, if you remember the symmetry in the numerator and denominator, although we spoke about denominator at length, I told you, right, there is a symmetry in the numerator and denominator. If you see here, the items within the brackets are the same for both the denominator, only the scalar changes. And we'll talk about that. That's also a natural segue when you find about Cramer's rule. The Cramer's rule comes when you apply the whole thing on the numerator also. That's how the Cramer's rule is derived, and I already put a video explaining that. And once you watch this first, you'll appreciate that. And the symmetry will also help us explain what is the adjoint and how to find the inverse of the matrix, which is a more important topic. So that's kind of a wrap up on this, on how we understand and how that leads or paves the way for the next video where we'll be talking about terms and terminologies. Hopefully this video was useful and you could get some sense on how things are getting connected. I'll see you in the next video on minors, cofactors and adjoint. Till then, stay tuned. Signing off on Clear My Paper. I'll see you in the next episode.